Welcome everybody to the start of the Chapter 12 discussion, and we are going to go over the first half of Chapter 12 today, and we are going to start taking the flip-flops that we've been learning about and cascading them into one another to create bigger registers where we can store more than just one bit of data at a time. This is going to allow us to create what are called counter circuits. Okay, so let's go ahead and get started here. So we are now to the point where when we are using a mixture of the flip-flops and the combinational logic gates, we are in sequential logic. So these are used all the time, used to count events, pretty much count anything, something going from low to high. It really doesn't matter. You can count just about anything. You can also count the time duration of some process. So, anything you can imagine that involves keeping track of time, keeping track of count, we can use these sequential logic circuits. And we say sequential because they follow a predetermined sequence or are triggered by a timing pulse or clock. So everything moves at the same time, essentially. So it says normally count in binary and can stop or recycle. And by recycle, we mean count, for instance, 0 to 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. That's what it means to recycle. It repeats the count over and over and over. So we can count to a certain number and stop, or we can count to a certain number and then count to that certain number again as many times as we need. The modulus, or the mod of a counter, is defined by how many counts there are. I mean, that's the number of binary states, but I always remember it by how many counts there are. So a mod 7 counter would have 7 counts. Now, typically we start our counts at 0. You don't have to start them at 0. There's ways that you can preset a group of flip-flops if you wanted to, and count from 2 to 7. But typically we start our count at 0. And so in the case of a mod 7, your count would be from 0 to 6. Okay? The example given here is a mod 8, where you count from 0 to 7. Okay, so it says the counter outputs are usually flip-flops as they can hold a binary state. That's what I just referenced. So as you see here, it could be a push button, it could be a motor encoder, it could be some kind of a repetitive clock waveform or some kind of trigger source that activates the counter and increments the count for each time this thing gets triggered. So in this case, we have a 3-bit binary counter that goes from 000 to 111. So this is what I just described down here. That is a mod 8 0 to 7 counter. Okay, so there's, that's as far as it can count, 000 to 111, right? And this would be the truth table for such a circuit, where we have a count that goes from 0, 1, 2, 3, 4, 5, 6 to 7, and then it repeats 0, 1, 2, 3, etc., etc. So this type of counter will repeat over and over and over and self-recycle itself. Right? So you can see how that works down here. So if we have 3 of them they're not really in series, they're cascaded together, and we'll show what those connections look like here shortly. But internally, you have the least significant bit, the second most significant bit, and the most significant bit. Okay? So this is the one that's going to change most often. So this is the one that's directly connected to the clock. Right? So Q0 is going to change most often because that's the first one in line. The output of this Q becomes the clock input of the next flip-flop. So this one, because the frequency is half of the previous flip-flop, this one changes half as often as Q0. All right? This Q now becomes the clock input of the next flip-flop, and you can see that this one changes half as often. So we get this natural progression from 000, 001, 010, 011, 100, 101, 110, 111, and finally recycle back to 0. Just by the nature of how flip-flops work, if it was a 4-bit, then we would have 16 counts. If it's a 2-bit, you would have 4 counts, right? You would have 0, 1, 2, 3. That would be your 4 counts. If it was a mod 2, it would just go 0, 1, 0, 1, 0, 1. And essentially, each time that you create a flip-flop, that's a mod 2 flip-flop. if we talk about, what we did for, I think it was chapter 11 in the lab, where we had just one single JK flip-flop, or this could have been before that. This could have been chapter 10 or 11. I can't remember. I think it was chapter 10. So the chapter 10 lab where we had just a JK flip-flop and had just the inputs and outputs attached to it in Quartus and then ran it, okay? That's essentially a mod 2 counter because it has the binary, if it's in toggle mode, it goes from 0 to 1, 0 to 1, 0 to 1, 0 to 1. So, that's the only 2 counts that it outputs, but technically that qualifies as a mod 2 counter. Okay, so here we've got, this is not really a counter, this is just sequential logic, where we've got a few of these gates that are in here, and we also have that connected to a flip-flop. Okay, so I'm not going to walk through this one. You can walk through this diagram on your own. You can see how everything changes, and we've got this flip-flop that can hold the state of a bit, and so like when this Q is connected to this input, this is always the input on this gate, so it's no longer just A, B, C, D. Now it could be the output of a flip-flop. All right, so again, just more. These two things are looking at the same circuit, right, with just slightly different input stimulus. This is another one. This is where we've got this one in toggle mode, right, because J and K are high in this JK flip-flop. We've got the asynchronous reset tied high, so we're not using that. And then the asynchronous set is attached to some input. So it's possible that we could drop a 1 in here and cause the output to go high. Okay, and so there's some clock pulse that comes here. So we have a couple different ways that this one flip-flop can control the rest of this circuit over here. Okay, and more. These are all in reference to this one single circuit here. So you can walk through those yourself. So let's go ahead and talk about the ripple counter. Right, because this is what I'm going to spend the majority of my time on, because I want to get to the point where we are creating these divide by n counters, and you should feel comfortable whether I tell you to do a mod 17 or a mod 4. You just need to determine how many flip-flops you need and what are your reset conditions. So before we talk about that, we're just going to talk generically about a ripple counter. And this is what I was referring to, where we cascade the Q output of one clock, of the output of one flip-flop to the clock input of the next flip-flop. So each successive flip-flop is essentially dividing that frequency by 2. So three flip-flops for a 3-bit counter. It's always this 2 to the n. However many flip-flops you have, that's how many different combinations you have. So if you just have one, if you just have one flip-flop, that's 2 to the first. That's 2 different combinations. If you have 2 of them, that's 4. 8, 16, 32, 64, etc. So, you can have a pretty big counter just using 4 or 5 flip-flops. Right, so a 3-bit, if we're just going to stick with this example here, a 3-bit counts from 000 to 111, as I described a little while ago. The modulus is 8, and we typically call it like a mod 8, mod 9. That's the terminology. And this is what it looks like. So we have each flip-flop in toggle mode. The J and the Ks are all high. And then we have the output Q become the input CP of the next flip-flop. Now notice these are all negative edge triggered. These are 74 LS76s, so that's the way they come if you buy them. So these are all in toggle mode. We have an asynchronous reset tied together so that if we put a low on this input here, it's going to clear out all of these and start it back at 0. So we have a mechanism now to where no matter what count we're on, if let's say we're on count 6, we could hit this asynchronous reset and clear everything back to 0. Okay? So we're just pulling, here's the least significant bit because it's the very first one. The most significant bit, remember, is the one that changes least often. So be careful when you name these, because I will probably ask you to draw some type of mod counter on the exam, and the biggest mistake is that you'll start off, this very first flip-flop, call this 2 to the second, 2 to the first, 2 to the 0. So make sure that you keep that straight, because the least significant bit is always the one that changes most often, and that's right out of that very first flip-flop. So this is what it looks like. So we have a clock pulse that's going into this very first flip-flop, and remember, the Q is the clock pulse of the other two. We have an initial asynchronous set that initializes everything to 0. Otherwise, we don't have a count to start from, right? So this is what I was trying to iterate with the other flip-flops, is that if you don't have an initial state for Q to toggle to, like if you have a JK flip-flop and it's in toggle mode, the output Q is only known if you know what the state of Q was before, because it toggles to the other position. So you need to know whether it's high or low. This asynchronous reset allows us to have that initial 0 value. So we put that initial reset in. Remember, this is negative edge triggered. That's why all these lines are on the falling edge of this clock. So there's the falling edge, falling edge. So you can see here, the falling edge of the first transition here, that's going to cause the first flip-flop to transition low to high. All right, now remember, these are negative edge triggered flip-flops, so this one is not going to change until the previous output Q here goes from high to low, right? And that's why it takes, you can fit 2 of the clock pulses into one single period of this output here, right? Same thing with this one. You can fit 2 of these into one of these. So you have to wait for the previous flip-flop to transition from high to low, and then once that happens, that's going to cause this one to transition, okay? Now, the next time it happens, this one's going to go back low, this one stays high, all right? This negative edge is going to trigger this again, and so now this time, this one is going to go from high to low. That's going to cause this one to transition, and this one going from high to low is going to cause this one to transition, and that's the cascading effect. The first one to change is the one closest to the if you were looking at this on a timeline, this one would change first, this one would change second, and this one would change, well, you have to wait up here for it to change, but if you're just looking at these two, this one will change first, and then that will cause this one to change, okay? So in the Kleitz example here, he's showing it happening, sort of instantaneously, but however long the propagation delay is from this thing going from high to low, and from this changing from the input to the output, whether it's 10 to 20 nanoseconds, whatever it is, there's a slight little shift there. And that's going to become important because the more flip-flops that we put in the cascade here, you're going to keep building that propagation delay with each output, right? And so that can be a problem potentially. So as discussed before, the state diagram, how many different states does your counter have? How many different states does does a stoplight have, right? I mean, you could do a state diagram for almost any machine or program, right? My favorite example of the state diagram, which as we tick off in time becomes less and less relevant, but that's the idea that you used to put money into a soda machine or a Coke machine to buy a Coke or a Mountain Dew or whatever. So back in the 90s, the price, I believe, was around 50 cents. Okay, maybe I'm thinking the late 80s. I don't know. But anyway, it used to be 50 cents. And so the example that I used 23 or 24 years ago was based on a Coke costing about 50 cents. And so the state diagram isn't a nice round circle like this where, I know here's my state, here's my next state, here's my next state. The way that we did it was, in terms of how much money you've put in the machine. Okay, so you could call that state 1 and state 2, but really I had state 0 cents. I had another bubble called 5 cents, another one called 10 cents. So I had from 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. All right, and then you have to account for the fact that if somebody already has 45 cents in and the last coin they put in is a quarter, that's going to be what, 70 cents. So you still have to account for some states that are above 50 cents, right? Because then you have to do something about the change. So when you look at the state machine of one of the old Coke machines, and you look at where all of the lines go, and here it's pretty simple, right? As long as the asynchronous reset stays high, right, you just keep counting in order. But what happens if you're at 0 cents? There's 3 possibilities to get to the next state. You could put in a nickel, you could put in a dime, you could put in a quarter. So, out of your 0 position, you'd have 3 separate, right? No, so what if you put in a nickel? Now you're at 5 cents, okay? What are the options from there? You could put another nickel in and move over to this one, which is the 10 cent. You could put 10 cents in and get down to 15, or you could put a quarter in and get down to 30, right? So, you know, if you just wanted to work that out, follow the example that I just did and see, you know, just how much space it requires on a piece of paper, just for a simple device like a Coke machine, right? You know, trying to take into account the different values of coins that can be put in, okay? So this is what I was discussing a little while ago, and we actually have a formula for, you know, maximum frequency limitations, but let me explain this again. So this first flip-flop is waiting for this clock pulse to go from high to low. It's a negative edge trigger. Once that happens, because that hits the input of this flip-flop, right? The clock pulse comes in, and it takes time for the input to make a change on the output. Right? So if there's something that happens on the input that's going to cause the output to change state, it takes a little bit of time to do that. And if you remember from our discussion, we call that the propagation delay. So inherently, just by us using a flip-flop, there's going to be a tiny little delay there. Now they're calling, you know, they're saying that the low to high propagation delay. In other words, this case right here, this is a low to high, right? This would be a high to low transition. So one of them is quicker, one of them is slower. So it takes longer to discharge as opposed to charging, apparently. So 20 nanoseconds here, all right? So that's already built into this. Now when this changes again, all right, it's still going to take 20 nanoseconds propagation delay, but now that's going to be built into this next one. Because remember, the output Q is the input clock pulse of the next flip-flop. So that propagation delay gets fed into here because, you know, it won't even change until 20 nanoseconds. Now this one has its own propagation delay, and so by the time you get to the output of the second flip-flop, you've got twice the propagation delay now. And you can see what's happening. Now this becomes the clock input of the next one, and so it's not going to transition until 2 propagation delays later, and then it transitions. And remember, this one has its own propagation delay. So if you start cascading 3, 4, 5, 6, 7, 8, 9 of these flip-flops together, what you're doing is you're creating a giant propagation delay before that last flip-flop switches. If your original clock pulse is changing too quickly, you can actually miss one of those cycles because of the propagation delay. So we have an equation for that. The maximum frequency that you can put into the very first flip-flop is limited by the number of flip-flops and also the average propagation delay. In the previous example that we've been working through here, the low to high is 20 nanoseconds, the high to low is 30, so that's an average of 25 nanoseconds. So if I'm working through this, the maximum frequency for something with 3 flip-flops would be 1 over 3 times 25 nanoseconds. So 1 over 75 nanoseconds. And if I plug that into my calculator real quick, since I've got it handy. So 1 divided by 75e negative 9, that gives me 13.3 kilohertz. I'm sorry, megahertz, 13.3 megahertz. So, you know, if you have a 50 megahertz system, you better use an IC or you better use a synchronous counter because that's too much propagation delay for what you're trying to do. So there is a limitation to this. Right? This is a 4-bit, and the only difference between this one and the other one is you just double the amount of counts. So a 3-bit, you can see it, it's working itself. You know, it hasn't changed. If you ignore this very last flip-flop, 2, 0, 2, 1, and 2, 2, essentially just repeat over and over as a mod 8 counter. It's just that now you've added another output, and so you've doubled your count. Okay? So in this case, we're counting from 0 all the way up to 15, and then 0 through 15. If you want to go the opposite direction, in other words, if you want to count down, the easiest way to do that is instead of pulling your outputs from Q, pull your output outputs from Q naught. That is literally the only change. Nothing else changes about the way these cascade into one another. The only difference is when we do it here, we pull, if this is a low to high counter, or an up counter is what we say, then all of your Qs are pulled, all of your outputs are pulled from the Q. If you want a down counter, all of your outputs are pulled from Q naught. Now, if the JK flip-flop you're using, like in Quartus, doesn't have a Q naught, you need to put a NOT gate off of this Q right here, okay? And then you can get your Q naught, and that will count you down. It'll start at 1 1 1, and then it counts itself down to 0 0 0, and then it resets and goes to 7. So 7 6 5 4 3 2 1 0, 7 6 5 4 3 2 1 0. Okay, and so now we are into the design of divide by n counters. So if you've been paying attention, you may have asked yourself at this point, well, what if I don't want to do a count to 16 or a count to 8 or a count to 4 or 2 or 32? What if I need a mod 19 counter? What if I need a mod 7 counter? Right? So now we have to do something about that by putting in some reset circuitry. Okay? So we know that if we just leave this stuff alone and we don't have any resets at all, this thing is going to divide by, in this case, it's going to divide by 16 because there's 16 counts. So, you know, from the clock pulse here to here, that's a divide by 16, okay, because it's a mod 16 counter. In the previous example with the 3, this is a mod 8 counter, and so this is a divide by 8. Okay, so what if you want to divide by a different number, right? What if you wanted to divide by 5? So you can see here, now we have what's called reset circuitry that will reset all of these down back to 0 if certain conditions are met. Okay, so what we've got this connected to is the most significant bit and the least significant bit. Now this is a NAND only because these are active low inputs. That's the only reason. If those were active high inputs, this would be an AND gate. But since those are active low, that's why we're using a NAND, because we want the operation of an AND gate. It's just that we have to satisfy the active low here. Okay? So this says it resets the flip-flop to 0 when 5 is reached. Okay? Now this is a mod 5 counter. It's going to count from 0 to 4. 0, 1, 2, 3, 4. That is 5 separate counts. So what's happening here is after it counts 0, 1, 2, 3, 4, 5, right? This one is going to be high and this one is going to be high because binary 5 is 1, 0, 1. That's going to reset all of these back to 0, and my count is going to restart. And then I go 0, 1, 2, 3, 4. Briefly, I mean, you know, nanoseconds, 5 is displayed and then it resets back to 0. Right? So you can actually see this glitch happen. So even though it's a mod 5 and you're only counting to 4, technically behind the scenes you're actually counting to 5. It's just that you're glitching on 5. When that first, you know, so here's zeros, here's 1 0 0. That's 4, right? As soon as it goes 1 0 1, however long it takes for that signal to propagate through this NAND gate and change the asynchronous reset and change the Q, that's all the longer it's on, because then it resets everything to 0. So the way that I say this is, let's just use the mod 5 here. So a mod 5 counts from 0 to 4 and glitches on 5. If I had a mod 10, it would be a mod 5 counter counts from 0 to 9 and glitches on 10. Right? So no matter what mod you're talking about, you're going to glitch on that number if it's an up counter, asynchronous counter. Okay. Notice what else happens here if you're, you know, let's say you power up and for some reason there's a 1 1 1 on the output or there's a 1 1 0. That's outside of this count here. But what happens is because you're not glitching, right? The only way you can reset is if this one's high and this one's high. And so in that case, that's not going to happen until you get this one right here, right? And then, you know, it's going to automatically reset itself. So if you're at either one of these, it's going to continue the count to 0, and then it will restart in here, all right? But we have a way to prevent this from happening by using an automatic power reset. We talked about that, right? So we can make sure that this has an initial value by using that automatic power up circuitry. And there it is. So we still want to, in this case, this is a mod 6 up counter with a manual push button reset. So it's automatically going to recycle itself if this one and this one are high, right? Because that's 1, 1, 0. That's 6. So we want it to glitch on 6. Now notice here we're not using the NAND gate. Whatever the last gate is that resets everything has to have an inversion on it because of the active low. So it just happens in this case we're allowing this to reset it, or we're going to let this manual push button reset it. So either one of those will cause this to go back to 0, right? We want the automatic operation of the mod counter, but we also want the ability to push this at any point in time and reset it. Okay? So, you may have to do something similar if I ask for this on an exam. And the most common mistake here is because you just heard me say here that you have to have a NAND, that really what you have to have is you have to have an inversion before you touch these reset terminals. Okay, so whether that's, if it's just a straight reset like this, or if you have the option to do something else, right? The final logic here is an OR situation because you want this or this, right? But here, remember, like I said here, you want the AND operation. It's just that you have to use a NAND because you have to account for the active low, right? So here, we're not accounting for the active low because it's going to be either this one or this one that gets it done. All right. So now there are 3 IC chips that I want you to know, and they'll be the only 3 that I ask you to know. There will be more IC chips that I ask you to know, but these I really want you to get because they're going to be the basis of everything in the rest of Chapter 12 and of 13. Okay? So, a 7493 is the first one we're going to talk about, and why would you do this as opposed to wiring up a bunch of flip-flops? Well, because this stuff is already wired internally, and you don't have to worry about you making a mistake. There's much fewer ways that this thing can fail as opposed to you cascading and wiring a bunch of flip-flops in series with each other, like a bunch of 7474s, 7476s, let's say. So the 7493 is a mod 16 counter, total. That's what it can do total. Right? Now, the way that it's broken up is it has a divide by 2 section and it has a divide by 8 section. Okay, so if you were to take this Q, you can see the internal diagram here of this. If you take this Q and pull it around here to this CP1, now you've just made a mod 16. So the way that this is set up is for, if you had a very, very small count, if you just needed a toggle, then you could use this Q0. That's your divide by 2. You don't need to worry about the rest of this. You just want something that toggles high, low, high, low, high, low. If you need to keep track of a count and it's between 0 and 7, you can use Q1 through Q3, right? It's got its own separate clock here, okay? Now, if it's something between 8 and 15, now you got to take Q0, pull it around to CP1, and now you can work with 4 bits all the way up to 15. And you still have this reset circuitry down here that's AND. So in this case, if you wanted to do something where you ORed something together, you would have to come up with some other logic as opposed to what you see here, because internally that NAND gate is already there. All right. So if you wanted a way to manually reset this, you would have to set up some external circuitry here to make that happen. Maybe what you do is tie one of these always high, and then have the output of an OR on the other side, right? Because then the AND gate is really being controlled by the OR, okay? But anyway, you can, this is great if you need to have a hex counter. For some reason, if you want your 7-segment display to count from 0 to 9 and then from A to F or A to E, you can do that as well. The next one, well, let's talk about it with this slide here. So the 7493 can form any modulus counter less than or equal to mod 16. So if you don't care about some specific thing that you're doing, like if you wanted to do a clock, a digital clock, If you want to do a digital clock, you want to use a series of 7490 and 7492s. But if you just need to count from 0 to some number up to 16, or you can cascade the 7493s together. So you could put 2 of them in series with each other and get a mod 32. So if you don't care about the count, you can use a 7493. That's just an all-purpose mod 16 counter that can go from 0 to 15 with the 4 bits. A 7490 counter is what we call a decade counter. And the way that I remember this is because decade is 10 and 7490 ends in a 0. That's how I remember it. This has a divide by 2 and a divide by 5 section. And so if you notice from the previous example here, we've got a divide by 2 and a divide by 8 section. And so if you multiply those together, you get the divide by 16. Okay? And so here's that mod 16 connection if you wanted to get those upper counts. So this one, it has a divide by 2 section and a divide by 5 section. Now, that becomes very handy because at least as far as we're concerned, we only have 10 digits, right? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we want a number bigger than 9, then we use a combination of those other digits. We only have those 10 digits to choose from. So this becomes useful for scoreboards. If you're going to create a scoreboard for like a soccer field or for a basketball court or something, it's going to have to count from 0 to some number. And, each digit is going to count from 0 to 9, and then it's going to repeat. So a decade counter is perfect for those applications because you don't need to put any extra reset circuitry in. Now, you can do it. It gives you the option to have those resets, just like the 7493. But typically, if you're using a 7490, you're using it for a specific application where you want to do a BCD or a binary coded decimal number or a decimal number where you're counting from 0 to 9, 0 to 9, because you don't have to do any extra reset. Okay. The other one is called the 7492. And the reason I remember that one is because this one is a divide by 12, and 7492 ends in a 2. So the 3 I want you to remember are the 7493, which I don't have a mnemonic device for. Just remember that's the other one. The 7490 is the decade because 10 ends in 0 and 7490 ends in 0. And the 7492 is the divide by 12 because it ends in a 2. So this has a divide by 2 and a divide by 6 section. And so you might ask, why divide by 6? That counts from 0 to 5. So think about what application we use where we only have a value count from 0 to 5. How about the tens place of the clock, right? We count 0 through 59 and then reset back to 0, 0. So the tens place of a digit in a clock is typically done with a 7492. So you would have, more than likely, you would have a 7492 to represent the tens place, cascade that one into a 7490 for the ones place, and that would count from 0 to 59. Okay. So again, you can cascade these together in turn. You have to make the external connection again, but you can multiply those together and get yourself a divide by 12. If it's from 0 to 5, you can just use Q1 through Q3, just like the 7493. If you just need to divide by 2, again, you can just use the Q0. And if you need to count from, what is that? Count from 6 to 11, then you would, combine those together and get yourself a total of divide by 12, and then use the reset circuitry. Okay, so here's the logic diagram for the 7490. Again, it does have the resets if you need them. But again, typically you're using this for an application where you would not want to bother with this because you want the count to go from 0 to 9. Okay, same thing for the 7492. More than likely, you're not even using the first flip-flop. You're using these 3 because you want the count to go from 0 to 5 because it's the 10 place of, like a clock or something. Okay. Now, this next section here, I encourage you to go through the book. I've tried this before where essentially I read all of this to you, and if you just happen to be in the zone and following everything I'm saying, then it might work if I read it to you and tried to explain it. But I encourage you to sit down with this, with each one of these, right? So there's more than just these three applications here, 12.1, 12.2, and 12.3. But sit down and work yourself through how this is operating, okay? So this one is going to give us a 1 pulse per second. All right, that's the whole goal of this first one, is to get us down to a 1 pulse per second. And all we're doing is taking the 60 hertz signal out of the wall. So 60 hertz is 60 pulses per second. So essentially, we have a divide by 10 that gets us down to 6 pulses per second, and then we have a divide by 6 that gets us down to 1 pulse per second. Okay, so that's that divide by n methodology, where we're taking some count and we're reducing it and dividing it by a certain number. So the goal here with Kleitz is that he's saying you can go ahead and just build yourself one of these and get your own little clock that produces 1 pulse per second. Now, if you're not familiar with transformers, I don't suggest you do that. But if you are a hobbyist, you could make one of these with just a few components. Okay, now you want the Schmidt trigger in there because that's going to fine-tune the release from this Zener diode here. Okay, it's still going to have a sine wave output, even though the Zener diode will only conduct 0.7 volts in the forward bias direction. Anyway, the Schmidt trigger here, as you know, puts nice crisp corners on everything. So that's important if you want this to be, the intention here is that you build this and then you can go ahead and build all the rest of this stuff because it uses the 1 pulse per second from the wall. So like I said, I encourage you to look through these. Here's an example of something that goes from 000 to 999. And if you use 3 7490s, you don't have to have any reset circuitry at all. Okay. A few more of them. There's a digital clock, and this one I would really encourage you to go through because this one goes over what I just explained about having a mod 10, a mod 6, a mod 10, a mod 6. So there's your seconds, there's your minutes, and then here's your hours, right? This is a military, or no, this is from 0 to 11, right? So we have a mod 2 because we don't have 20 o'clock. We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we go back to 1. So a 12-hour clock is even more odd because you don't use the 0 condition, unless you're talking about a 24-hour clock. Okay, so now what I want to do is I want to go to the board, and I want to do a few of these and just walk through my process on how to create any mod counter that I ask you to come up with. All right, so we are going to go ahead and try to do some of these on our own and see what we come up with. Make sure I have my good marker here. I think this one will work. Hopefully I didn't take the other one somewhere. Oh well. All right, so let's start with something with just a few of these and go with a mod. Oh, let's say a mod 6 counter. Or not a mod 6. Let's do mod 3. Okay. So this is going to count from 0 to 2, and it's going to glitch on 3. All right. Now, I know my count is less than 4, and it's more than 2, so I'm going to have to use 2 flip-flops here. So there's my J, K, Q, Q naught. I'm not gonna worry about the asynchronous set and reset here, or I'm sorry, the asynchronous set. Okay, that's gonna become the clock pulse of the next one. Q is gonna become the clock pulse of the next one. And this one has its original clock pulse. And you could make these negative edge triggered if you want to. Tie all these high. Put them all in toggle mode. Okay. So glitch on 3. 3 is 1, 1 in binary. Okay. So in our case, that's 0, 1, 1 because we do have 3 bits here. Okay, so actually, now that I think I just said this, I don't even need this third one. We just need 2. I don't know why I drew the third one. so tie that high. All right, so it's when both of them go high. So actually, that's not a very, it's actually 0 through 2 is going to give us 0, 0, 0, 1, 1, 0. Okay, and we want to briefly glitch on this and then return. So we're going to glitch on this. So it's when, if we take our resets here, and we have our NAND gate, when this one goes high, and when this one goes high, we are going to take that to this asynchronous reset. Okay. All right, let's try a different one. Let's try one with more counts. Mod 11. Okay, so that's going to count from 0 to 10, and that's going to glitch on 11. Okay, 11 in binary is 1, 0, 1, 1, because 1, 0, 1, 0 is 10. Glitch on 11. Okay, so that's going to require 4 flip-flops. All of them are in toggle mode. Right? And so the Q becomes the clock pulse of the next one. And we have our J's and K's. And we show that this is in toggle mode by putting them all high. And again, you could make these negative edge triggered, but just for this example. Okay. So we need to set up how we're going to reset things here. So if we're glitching on 1, 0, 1, 1, that is when Q3, Q1, and Q0 are high. Remember that this is Q0, Q1, Q2, Q3. Q3 is the most significant bit. Okay, so we could use a 3-input NAND gate, but what if you only had 2 input gates? Okay, so what if this was already hardwired in, like we saw? Okay. So let's say we have no choice. We have to use this last NAND. All right, so it's no different than what I asked you about earlier, where, you know, how would you make a 3-input gate out of using just 2 input gates? Same thing applies here. I can take my Q, let's take Q0 and Q1 and AND those together. So I'm going to take Q0 and Q1, and that is going to become the input on one of the gates, and then the other one I'll just connect to Q3. Okay. So I'm ANDing these two together, and then I'm taking that result and ANDing it with this, and then, you know, inverting the output is the way that we should look at this. Okay, so that will get us a mod 11 counter. Let's do another one. How about a mod 9? Or how about a mod 13? So that's going to count from 0 to 12. We're going to glitch on 13, which 13 in binary is 1101. So it's going to look fairly similar. Those are all high, J, K. Asynchronous reset at the bottom of each. And a Q out of each one. This is Q0, this is Q3, this is Q2, this is Q1. Okay? So this is Q3, 2, and 0 all need to be ANDed together. So this time I'm going to allow myself the luxury of having a 3-input NAND gate. Okay. So then I just need to make sure I grab 0 and 1 and not 1, sorry. I'm grabbing 2 and then 3. Okay? So Q3, Q2, and Q0. That's what's going to reset this and give me my mod 13. Okay? What about, let's take it even further and say we want a mod, how about a mod 28? Mod 28, that's going to count from 0 to 27. Glitch on 28. All right. Well, let me think about this. There's going to be 16 plus 8 is 24. Plus 4 is 28. I think that's it. 16 plus 8 plus 4, because that would be 2 and 1. So 16 plus 8 plus 4. Is that right? 28? Yeah, that's right. 28. So there's the binary. So I'm looking for Q4, Q3, and Q2. I don't care about Q1 and Q0. So here we go. I got to leave myself room for 5 of these. I'm doing this every time just so you can see. This is the habit to get into when I ask you to draw these, so you can do it. So this is Q0, Q1, Q2, Q3, Q4. Okay, and so the asynchronous reset at the bottom of each of these. And let's see, I need a 3 input, don't I? I'll let myself have another one. I'm going to put it over here to make it easy on myself too. So again, all the resets get tied together. Here's my 1, 2, 3. And again, I need Q4, Q3, and Q2. So Q4, Q3, Q2. Okay? All right. So it shouldn't matter what mod I ask for. It should be pretty straightforward about how you get to that count. And you have to make a determination first how many flip-flops that you need. And then second, you need to figure out what your reset circuitry is going to look like. Okay? All right, that's it for this section.